So for the transportation problem, we are looking at, and for our course, I'm just going to keep this common notation of saying our supply points typically are called warehouses, and actually people typically just say W1, W2, W3. And then our demand points, where you want the goods shipped to, I'm just going to label them as store just because warehouse and store are easy to remember in terms of direction of how goods are being shipped. And people often call this S1, S2 when they're lazy. Okay. We have some sort of cost associated with shipping the goods between the warehouses and the stores, between the supply points and the demand points. And your supply points will have some sort of supply attached to each one, so specifically the supply of each that each has. Similarly, your demand points will have a demand associated with each one. And the goal, here's the key thing, the goal of this problem is we want to ship from our warehouses the goods that each of the stores want. And specifically, we want to minimize the total transportation cost. So one of the ways to think about this is maybe these different warehouses all belong to the same company. So what they have to do to minimize their overall cost and then behind the scenes maximize their profit is what they want to have the cost of shipping out to be as little as possible, and they don't care what warehouse it ships from as long as they actually have the goods at each warehouse to deliver. Okay. Now, we did a lot on Friday, so I am going to hand wave through it. Okay. So the first thing that you have to do is you have to set up a Tableau. Come, stop freezing on me, screen. And the Tableau goes as follows. You make a grid of warehouses as the rows, stores as the columns, and if you've looked at the homework already, which some of you have and hopefully more than just a handful of you have, what you'll notice is in terms of when you're given this information, it is typically not given as a bipartite graph. It is also given in that chart. And that chart is typically like one step away from your initial Tableau. Okay? So how the Tableau is made is it totally looks like just a spreadsheet. In each of the cells is going to be how much goods ship along the edge associated with the individual cell. So this first cell, remember, represented the edge that went from warehouse 1 to store 1. And we're trying to figure out how many units of goods are going to be shipped along that edge. Inside of these little guys, and we said that you could either do it like a little triangular shape or a little square shape. Different books do different conventions. I forget which your book does off the top of my head, but definitely the one that looks like a triangle is quicker to do if you're in a hurry. But I have to admit, when I first started doing it, I liked the squares. I just felt that they looked better. But it doesn't matter. As long as somehow you have a line that keeps this number away from everything else. Why? Because this little number in the corner here is representing the cost to ship goods along this edge, and then we're going to have a second number in the cell that's the amount of goods along the edge. Along the outermost row and column gives you the total amount of supply in each warehouse and the total amount of demand that each store wants to have. And the key thing you have to have is when you're setting up the initial Tableau is you need to have a balanced Tableau, and that allows our algorithm for finding our solutions to work. Okay, so this one here we found last time was not balanced because if you add up all of the supplies, it was greater than the amount if you added up all of the demands. And in fact, it was off by, I believe, 20. So this was 130, this is 110, so it's off by 20. So if the total supply that you have is greater than the total demand, the fix is to add a fake store. So we added a fake store, and the amount of demand from that fake store is going to be all of the leftover supply that isn't used. Balance is actually a technical term, balancing the Tableau right here. So if you see that buzzword of balance, find a balanced Tableau or balance your initial Tableau. It is talking about making sure total supply equals total demand. But in terms of, even though it's one of the technical terms, it is totally a descriptor. It's one of the things in math. Our names are typically descriptors or named after somebody. The balance here is saying supply, demand. If you put it on like a, I don't know, like a teeter-totter, it's got to level out. But yeah, that if you're thinking yes would be the quick answer. These here, the little numbers here are considered the labels on the cell, and they are the cost associated with traveling along the edge associated with the cell. Once you balance your Tableau, key thing is your fake store, the thing that doesn't really exist, officially called a dummy store, but unless you've played like cards and dealt with dummy hands, the descriptor of a fake store typically cues you in clearer of what it is. The cost associated with traveling to this fake store is 0 because it's literally just leaving the goods in the warehouse. You may. So in terms of if you see one of these guys, it is fair game to have a fake store in there. Oh wait, you said fake warehouse. We are not going to worry about, sorry, I didn't read the second line with the word warehouse there. We are not going to worry about that quote-unquote fake warehouse. So for us, we're always going to have the situation where the supply is either equal to or greater than the total demand. And that's just because you have to worry about an extra thing in dealing with your solution if you have it unbalanced in this opposite direction. So that would be setting up your initial Tableau. Then you have to set up your initial solution. And in terms of what you would see, what I typically do is set these guys up into 3 parts. The first part is set up your initial Tableau. So be looking for this. And the second part would be something like in the directions, use the northwest corner method to get your initial solution. Okay? And remember what the northwest corner method was. It said you look in the northwest corner, north meaning up, west meaning to the left. So here our first thing that we added in was that blue 40. Why did we grab 40? Because we tried to get the maximum amount that we could ship along warehouse 1 or from warehouse 1 to store 1. So we looked at the total supply in warehouse 1, the total demand of store 1, and if you take the minimum of the 2 values, that's the most you can put in any one cell. Why? Because the sum across the entire row has to equal the total supply of the warehouse, and the sum across the entire column is the total demand of the store. Okay? Once you go ahead and enter in your answer, either the row or the column will zero out, sometimes both, but typically just one. Once one of your row or column zeroes out, you never use that row or column again. If both of them zero out, you only eliminate one row or column, so you get to pick which one you want to keep. Okay? And then we just iterated that process until we got the rest of these numbers, and we adjusted the supplier demand as we went. This now was our initial solution. There was no guarantee that this minimized the cost of transporting goods along those edges. This was just a way to transport goods along from warehouses 1 through 3 to stores 1 and 2, where we actually met all of the demand and, well, let's face it, had 20 units of supply left over. Okay. So that was the initial solution. The next thing that we did, and this was really the thing that we ended on last time, is we calculated things called selling prices. We calculated the U and the V, and we talked about some of the theory behind it. But the thing that you want to keep behind, the thing that you actually want to remember is this bit right here is that formula. Even if you don't remember what the U and the V are, don't worry about it. Those are totally just conventions to help you figure out which edge you want to keep, which edge you want to toss out of the current solution, which edge you want to add into the current solution. So at whatever step you're at, when you have a current solution in the transportation problem, when you then iterate to seeing if you could get a better solution, you're always removing one edge, so removing one cell from the solution, and then adding one new cell in. Okay? And we're going to use these formulas right here to make that work, that highlighted formula. Okay. So we took our initial solution that we got by way of our northwest corner, and we used our formula that I highlighted and then recopied when we did it on Friday. And we said, all right, the cost, so the guys inside the little triangular labels, equals this U and the V, and the subscripts are reversed here. Okay. We automatically set U 1 to 10. I believe your book does 10. It's common to do 1 or 10, which I told you before. It's also common to do 0 as well. I just did 10 because it makes your numbers look nice. Okay, you don't have to worry about decimals as much. Actually, you wouldn't worry about decimals as much before either, but this is a nice way. 10 is a nice number. So then once we had U1, we created all of the formulas from cost equals V minus U. So we created all those guys down, actually pulled the cost from the labels. And here's the key thing in this section. We're only doing this for the cells that are in the current solution. And with Tableaus, the way to deal with your variables or your cells or your edges that are actually currently in the solution, these are the ones in the Tableau that actually have numbers in the cells. So these 5 cells right here, the ones that are in the solution right now, or what we call our basic variables. Okay? I don't care if you remember basic variables. That's something you'd need if we were in an operations research class. Since this is literally our last day of class, the only thing I care that you remember is the number. These are only on the cells that we actually have numbers in them right now. Okay? We then solve for all of the u's and v's, and once you have the initial guy of u1 equaling 10, you will be able to solve for everybody else as long as you actually have a solution. As long as you have an underlying tree in the bipartite graph, you'll be able to solve for all of these guys. Okay? Now, what did we do with them? We then said how to determine which new edge to add to the solution. We used the following formula, and the following formula looked almost exactly the same as that cost formula that we were dealing with to solve for U and V, except here what happened, we actually looked at how much we could increase our overall cost. Okay? So this formula is different than the one in your textbook, and that is because your textbook is dumb in that section. Yeah, so to answer the question, you are, for U1 here, that is just a random number. You could actually change it out to 100, to 1, to 5, to whatever number you want. For my sanity, if I'm grading these, I would prefer you to set it at 10, just so that I can get consistency on numbers here, but you can actually set it to anything you want, and the only thing that would change is your U's and your V's would be scaled up or scaled down appropriately to how you and your classmate changed up on your U1s. And since we don't actually care what these values are for the U1, the U's, and the V's, all we care about are which edges we're adding into the system or deleting from our solution. That's why we can set this to an arbitrary value at the beginning. If we were a little bit more of an economics-focused course, there are ways where you can actually pull a very reasonable answer here. Technically, it can still be random, but sometimes people want this to more accurately reflect their specific situation that they're modeling. And they'll still get the same answer either way, though. All right, so to add the new solution, we're going to look to see how much we can change our total, how much adding in the edge will change our total cost. And this formula right here with the Cij with the tilde is going to give you how much adding the new edge ij would decrease your total cost. Now, watch out. When we were finding the U's and V's, we only dealt with the cells that had solutions, so only had numbers in them. Now, when we talk about adding in the new solutions, we're only going to look at the non-solution edges, so the ones that had nothing in them. Okay? So this is what we ended on last time. You took the U's and the V's that we found previously. That previous step was only solving for these U's and V's to get to the current thing we're looking at. And we already have the cost of the C's without the tildes. Put them into the formulas, calculate the values, and you look for the maximum value. It's easy to spot a maximum value, which is why I did this formula in this way. Actually, a number of textbooks do it in this way. Yours just doesn't. Okay? So you look for that maximum value, and this 3 tells you that if you actually add in the edge associated with warehouse 1 shipping to store 2, or you put x12 into your solution, the total cost should decrease by 3 units. Okay? We also mentioned what happens if you're dealing with a negative number. This negative number tells you that if you add in the edge from 1 to 3, so keep supply at the warehouse, you'll decrease your overall cost by -1. In other words, you'll increase your overall cost by 1, because subtracting a negative. This one down here at 2.1 says you'll decrease your overall cost with shipping. If you add in the edge, if you use the edge 1.3 by 1 unit, that means we'll probably need to do this step at least 1 more time to put this edge into your solution. And if you have a 0 right here, this means, yeah, throw in the edge, or have warehouse 3 send stuff to store 1, but it's not going to change the overall cost to the system, so why bother, is the personal comment there at the end. Okay? So we're going to look here, and we're going to say, hey, 3 was the biggest number that we had in play, so we are going to add in the cell 1, 2 to our solution. And if we add in a cell 1, 2 to our solution, we have to then remove one of the cells. So we ended before we got to how to remove a cell. So here's how to remove a cell. So when you're incorporating a new edge into your tree, what you're trying to get is a new spanning tree, because all of these solutions in the graph would actually correspond to some spanning tree, the way that they're sort of jagged here. There's lots of ways to read a Tableau. We're not going to go over it just because we don't have enough time to do that, but this one here does actually correspond to a spanning tree. So adding in a new cell is us attempting to get a cheaper spanning tree, but every time you add in a new edge to a current spanning tree, you close the circuit. It's just what happens when you have a tree, okay? Which means we have to remove an edge, and we remove one of the other edge is in the circuit we just closed, okay? Now, how do you find the circuit in the Tableau when you're not in a tree? Well, it turns out recognizing the circuits in Tableaus are actually something that can be done relatively frequently, okay? So here's the thing, is it's going to look like a loop, and in fact, we often call it find your loop. Okay? You have to have at least 4 different cells in this loop that will correspond to your circuit. Otherwise, it just doesn't happen in terms of the Tableau. And here's what has to happen for this loop. If you have any 2 consecutive cells in the loop that lie on the same row or column, I shouldn't say that. You have to have any 2 consecutive cells in the loop lie on the same row or column. If you look at any 3 consecutive cells in the loop, they're not allowed to all lie on the same row and column. And if you look at the first and the last cell in your loop, those guys need to lie in the same row and or column. And often I'll actually travel around in terms of these cells that I'm looking at clockwise, but you can actually go around the opposite way. It doesn't actually matter. Okay? So I'm going to throw this example to you guys. It is currently initiated up on Poll Everywhere. I'll share the second screen and then get rid of it in a little bit in case you guys need the URL right up there. And let me make it so you can actually see it a little better. And the question here is, which one of these 3 examples actually is one of these things that we're calling a loop in the Tableau? If it is one of these things that we call a loop in the Tableau, it will in fact correspond to a specific circuit in the underlying graph. So I'll give you guys a second, see if you think any of those 3 pictures correspond to a loop in a Tableau, and just to make sure we're all on the same page with respect to formatting, I just put a little grid here. These grid boxes in each of these 3 pictures represent the individual cells in your Tableau. I didn't try to do anything with labels because it was too tiny. And the little circles in each of the cells, whether it's 4 in the first one, 4 in the second one, or 5 in the third one, those are talking about the cells that we're actually trying to use in the loop. So those would be the cells that are in the current solution. And then the arrows here are representing the order of how you calculate your loop. So for example, on this first one, if we look at the upper left corner, maybe that's your first cell in the loop. The second cell in the loop would be go over, so horizontally, follow that arrow, and then the next dot would be the second cell in the loop, and so forth. When we actually get a Tableau, when we pick up our example again, we'll have the actual names of each cells, and I'll write out what the loop looks like when you actually write it out. Okay. So I'm going to go ahead and stop sharing the second window. It looks like I've forgotten if I've allowed you guys to respond more than one time or not. Just a second. Yes, so you guys can respond as many of those as you want. You can select up to all 3 of those answers. So each one is a, yes, I think it's a loop, no, I don't think it's a loop. Okay. So you can respond more than one time if you want to. So this is the thing where we talk about first and last cell. Is it would be different depending on which cell you could figure is the first one. So for example, in this first picture right here, if we pick the upper left corner to be your first cell, this would be like the first cell. Actually, I'll label it with a little 1, 2, 3. So this would be like make sure I can write just a second. So this would be like first cell, this would be like second cell, third cell, fourth cell. So last cell would be the last one right before you get back to whoever your first cell was. And notice here, you can pick a different first cell. You'll still have the same, in this first picture, same 4 cells that you're dealing with. It just your quote-unquote first cell and last cell would change up. Okay. All right, it looks like the guesses have mostly stabilized. Oh, that is a good thought. So the last question that came in asked if these loops are, when you look at them in the chart, if they basically look like a cycle where you're only allowed to have, I'm going to add in some extra words that you didn't say, but where they only have right angles and straight lines. And the answer is yes, that's a good way to think about it. In terms of the truth value of those 3 statements, statements 1, 2, and 3, it turns out even if you start and end your loop, if you picture it in a different location than somebody else does, like for example, pick 2 of you guys, if one of you started your loop in the same way that I did, but maybe somebody else started the loop over here, and this is the cell they labeled as 1, it turns out the truth value of this last statement is actually going to stay the same if it is a true loop. All right, so it looks like the answers have stabilized. Let's actually answer this question right here. And it looks like, according to your guys' responses, overwhelmingly, you guys are correct. Okay? So the first one here, and let me get this out of red. So this first guy here is a loop. Notice as we go around, start wherever you want to start. I'm not going to relabel these guys, though. Any 2 consecutive guys, so the first cell and the second cell are on a row. Second and third cell are on a column, same column. Third and fourth on the same row. Fourth and first on the same column again. If we take any 3 consecutive cells, you have to turn a corner. So this guy, totally a loop, it meets all 3 criteria. Now the second one is not a loop. Which criteria does it violate? 1, 2, or 3? Yeah, it actually turns out, depending on who you think the starting vertex and the ending vertex is, it would violate for sure condition 1, and then depending on who your starting and ending cells were, it would also violate vertex 3. So for example, if I label this upper left-hand corner as my starting cell, in this particular instance, the third criteria is not violated. But if you started your first cell, say, down here, it totally would be violated. Okay? Now, I'm also going to claim that this last guy is not a loop. What do you guys think? What condition is violated for this last example? You got it, condition 2. So it turns out that even though we said here 4 distinct cells, or 4 plus distinct cells, in reality, okay, technically speaking, you could have more than 4 cells in there, but it has this sort of twisty thing that happens. Most of the time, it is actually just going to be 4 cells, and it's totally going to look like a little rectangular shape. So no cells in the middle of an edge, no weird thing that makes it look kind of like a trapezoid. Okay. So that would be the idea. You're not going to get anything more complicated than one of these 4-cell rectangular type pictures. So let's apply this to our problem or our example that we've been working through so far. So at the end of last time, oh, I need to give you some extra information. So this is how to, so at the end of last time, we said we wanted to add in this new cell at row 1, column 2. Okay? So we're going to use this concept of a loop of we'll add in this cell, and then here's what we do. Okay. So what we're going to do is we're going to grab, looks like I've missed some words, so let me go ahead and deal with this. So we are going to grab the loop, so get, did not want that color, just a second. So we will get the loop that incorporates the new cell. And what we're going to do is we're actually going to adjust the amount of goods that we're going to ship across that associated loop, okay? So we're actually going to adjust the solution or the values of the solution, but only along this loop that incorporates the new cell. Now, along this loop, which corresponds to a circuit in the underlying tree, we're going to decrease the value along the odd cells, and that theta is the name of the circuit. And we're going to increase the value in the cells that are what are called the even cells. Now, here's the deal of how to find even and odd cells. Your even cells are always going to be your new edge, and then all of the cells in the loop an even number away from that new edge. So, for example, if we pick on this first guy right here, if that cell that we labeled with a 1 is actually the new cell, well, what happens, the other even cell would be this one over here. Why? Because it's 1, 2 steps away, or 1, 2 steps away. The odd cells in the loop are an odd number of edges or odd number of steps away from your new cell. So if this guy that we labeled the 1 before is our new cell, 1 step away would be at the cell we labeled at 2, and also the cell we labeled with 4. So notice this one is 1 step away. This one down here that we labeled as 4 is 1, 2, 3 steps away. Okay. So notice in terms of your loop, starting with your new cell, which is an even guy or tagged as even. I was trying to be even. That's a terrible way of writing even. Every other cell in the loop is even versus odd. That's another way to think about it. Okay. Now, remember, we're decreasing on the odd cells, we're increasing on the even cells, so notice what happens when you're shipping your goods. These guys that are even cells, the new cell has nothing that we're shipping on it, so we have to increase that one. But if we increase shipping in this cell, we have to decrease the shipping somewhere else. In other words, you have to move where you're shipping your goods between. Now, the actual circuit itself, oh, I did a lie earlier. Just a second. We're going to erase the lie. The value of the circuit, or that key value theta, not the name of it, sorry about that, got a little bit ambitious. The theta here is specifically the value that we're adjusting everything by. So this is going to be the value, is the minimum of the values currently in the odd cells. In other words, this is the maximum amount that we can pull from your odd cells and move into your new cell. This is sort of the idea behind it. Now, not going to lie, it's definitely easier to see this when you actually start doing it. So let me write one comment. Actually, we already talked about that one comment, so let's actually just do it. I have sticky notes to myself that say, don't forget this comment, it's super important. That way I don't forget the key things. All right, so we've got this. This was where we ended before. We had our initial solution. We figured out that we wanted to add the new cell here at 1, 2. So first of all, let's find our loop. So the loop that is going to incorporate 1, 2, you typically start with your new edge, and then we have to find the rest of the loop. So remember the criteria of your loop, and I'm going to go ahead and do this in orange so it's easy to see here. For sure, the new guy is in there. Then what has to happen? You're not allowed to have more than what? More than 2 cells in your loop on any row or column. Well, if we look down the column of star 2, notice there are 2 possibilities. We don't know which one to choose. Your loop is always unique. So if you have a choice going in either direction of a row or a column, don't go along the column first. Instead, we'll look along the row. So if we look along the row, what cell do we have to throw into this loop? Any guesses? And remember, you're only allowed to use cells that currently have values in them. So only cells that are currently in the solution, other than the new cell you want to throw in. Well, 1, 3 is this guy over here, so that's currently not in the solution as well. So that one you're not allowed to use. So you have to use somebody that currently has a number in it. So the only other guy on the first row that currently has a number in it is over here at 40. So that would be cell 1, 1. Now, it doesn't matter if you're going clockwise or counterclockwise around this loop. So since we picked up cell 1, 1 next, I'll go ahead and write it next. Okay. Now, if we go back up to loop, notice we have 2 cells in the first row. That means we should not have any other cells in this loop on the first row, which means we now need to look at columns. We still have an issue in column 2 because we don't know if we want to choose 2, 2 or 3, 2. But if we look now going from this cell 1, 1, who should we go to next in the first column? Remember, you're only allowed to pick cells that are currently in the solution. So that means they have to have numbers in them right now. Yep, so row 2, column 1. So this guy here, that 20, was the only other row that actually had a number in it. Now, once you have decided to put cell 2, 1 into the loop, what do we know? In terms of creating a loop, we have to go to, yes, we have to go to 2, 2 next. Why? Because we have to not go in the first column, we have to now go in row 2. Now, for row 2, we know we have to get to 2, 2, and there's 2 ways you can know that. One is this guy is the only other number in row 2, but even if he wasn't, we'd know we have to go to 2, 2 because 2, 2 is the only other cell that is both in the same column as our previous guy and our past one. So I'm going to go ahead and put this guy here, and at this point, we can close up that circuit. And this is how to actually write the loop, which corresponds to the underlying spanning tree in the bipartite graph. Now, when we actually want to go ahead and do our adjustments on the values of x, the values in the actual cells, not the cost, but the values. In other words, the 40, the 40, the 20, and the nothing. You want to label your loop odd and even. You always start with even, which is the new guy. Then everybody else alternates odd and even. Okay. We'll go ahead and we'll calculate our theta. So our theta was the minimum value across all of your who, the minimum value of all of your odd cells. Now in our case, our 2 odd cells are 1, 1, and 2, 2. Both values are values of 40. So it's pretty easy to calculate the minimum. It's just that same value of 40. Okay? At this point, what happens? Your even cells are going to increase by 40, and your odd cells are going to decrease by 40. Okay? I'm going to put that work actually up here in the Tableau. So what we would do is the new value right here, so we're going to add it to be 40. The value of the new guy is always whatever the value of theta is. So I'm going to go ahead and just put in theta equals. I actually don't normally do that, but right now to try to highlight that that's going to be the value of 40. The odd cells, so following the loop, 1 away, we're going to decrease by 40 on both of them, which zeroes both of them out. And then if we go and wrap around to the last guy, which is even over here, we'll go ahead and increase by 40. So if we add 40 to 20, we will get up to 60. And notice here these blue guys with the new values along those 4 cells. If you add across the rows, we still get to the supply of 40 and 60. And if you add down the columns, we still get to the demand of 60 and 50. This thing of adjusting around the loop or the underlying circuit in the what used to be a spanning tree and isn't currently, is a way to make sure you're still meeting your supply and demand criteria, or constraints to be precise here. Now, at this point, you then have to kick out one of the cells. So let me go ahead and get back into black. So then you remove the one cell whose value, the x part, so the value in the cell, equals 0. Now, this example was chosen on purpose because anybody notice what happened along that loop, along those 4 cells that we adjusted their values? Why would I say this is a little bit of a special case? Exactly, because there's 2 zeros. So what that means is you have to keep one of them because you're only allowed to kick out one cell per iteration. So in this particular case, so in our case, we must keep either cell 1, or cell 2, okay? So for the purposes of today, I'll actually keep cell 2. It didn't actually matter which one you decided to keep or not keep in your solution. I just went ahead and kept that one just because, okay? Now, what does that mean in terms of our Tableau? Actually, it means that my next Tableau is going to be pre-prepped for us, is why I circled that one. So what does this mean for us? This means at this point in time, we now have a new solution. It is no longer the initial solution, but notice what happened. These 4 cells now were adjusted by what we just did. We kept the 0 here because we were keeping the cell 2 in our solution, but the cell 1 was the edge that we removed. So these 5 cells right here correspond to a spanning tree in our underlying graph, even though we technically put a 0 on that edge in terms of how much goods we shipped across it, okay? So that is a trick that does happen to make sure the algorithm works just fine in this particular Tableau situation, okay? At this stage, you then repeat the process until we get to an optimal solution. Now, the question, of course, is what's the thing that we actually repeat? And the thing we actually repeat is the calculating of the prices to find the new cell to kick out of the solution, deal with the loop to figure out how to adjust these amounts in each of the cells, and then that's the part that we're iterating through. That's the part that gets repeated in the algorithm. So let's actually do this a little bit quicker now that we've talked through the process before. So at this stage, so we are now at a new solution, not the original solution, and no guarantees it's the optimal solution. We are going to calculate our prices. So calculate prices. And specifically, these are of the various cells in the solution. Cells in solution, or technically the basic variables. Okay. So here, what do? We're going to look at these 5 cells. So to remind ourselves of the formula, this is Cij is going to equal Bj minus Ui. Please note the subscripts reverse. So in the actual solution, we have 1, 2. So this would be C12. Let me go ahead and just write it in. So the cost of C12 is 2, and that's supposed to be V2 minus U1. In our solution, we also have cell 21. The cost associated to cell 12 is 6 up in that teeny tiny label, and this is V1 minus U2. We also have C22. This one has the cost of 7, and it is V2 minus U2. We also have in our solution right now 32. The cost for that one is 6, and this is V2 minus U3. And lastly, we have C33, and that is a cost of 0, and we have V3 minus U3. Next thing you do is actually solve for all the U's and the V's. So we'll go ahead and set U1 equal to 10. That means we can then solve for V2. from this first formula. So we've got V2 minus 10 has to equal 2, so that means V2 is 12. We now know V2 and U1. I don't have either V2 or U1 in this row, so in this formula, so we're going to skip it. So we come down here, we have V2, U2, so we can figure out U2. I'm on purpose leaving a blank here to remind myself to go back and solve for these guys. So V2 is 12, so 12 minus something is 7. What is that, 5? Next, so in terms of how we've gone, we progressed this way, then we jumped, then we went back up. So we can go back up now, and why would I know I can go back up? Because we got U2, which means we'll be able to solve for V1. So if we solve for V1, we have something minus 5 has to equal 6, so that should be 11. And then we can continue on down. Next formula we haven't used yet. We've done 3 of them, so this one, V2, we have V2, it's 12 right here. So if we have 12 minus something is 6, this means U3 is 6. And while I'm writing, anybody got what V3 is? Yep, it is also 6. Now when I'm doing this, when I'm doing it on my own, I don't normally put in all the arrows because these are really to help you guys to see what we're doing at which point in time. And I'll actually normally squish these a little bit more to the side. This one's a little bit more to the side, this is a little bit more central, because then I can do the next step right next to us, right over here. So I'm going to zoom in just a little bit and give us the space to actually do that. And the reason for that is sometimes it's helpful. It doesn't have to. So now for the non-solution edges, or the non-solution cells, or the technical term, non-basic variables. And this one, we're going to use the formula that, and I'll write it above here, Cij with a tilde, and this one is Vj minus Ui minus the cost in the cell. Okay, so this is the how much would the new cell decrease the overall cost if we threw it into the system. Now, at this point, you have to, or you want to, look at these cells that are not in the solution. So these are the cells that have blanks in them. Hint, we should not be throwing the cell we just threw out back into the solution, because that's just on a logic standpoint dumb. But if we did the math correctly, that shouldn't increase, or excuse me, decrease our total cost, because we already said it should get kicked out. So even though I'll go ahead and calculate this tilde for C, I don't want I there, for C11, it should not be one that comes into play. So this is V1 minus U1 minus the cost in cell 11. So here, notice we've got all of the work already for the U's and the V's. So V1 is 11, U1 is 10, and cost in this first cell is 4. This actually looks negative. So that would be 1 minus 4, so negative 3. So this tells us if we threw cell 11 back into the solution, we would actually increase our total cost by 3 units. And that makes sense because when we kicked it out of the solution, we said we were going to be decreasing our cost by 3 units. Okay? So this says you just would undo the work we just did. If we look in cell 13, now this is just leaving supply at warehouse 1, and remember warehouse 1 had the cheapest cost to ship out, so that one's, logically speaking, probably not going to get pulled into our solution, but this would be V3 minus U1 minus the cost associated. So V3 was what? V3 is 6, U1 is 10, and the cost is 0, so this looks like a negative 4. Negative values means your cost would go up. Never choose somebody that's got negative values from this C tilde. Now, other blanks. Second row, we have a blank. So this is C23. So we're looking at V3 minus U2 minus the cost in that cell. So V3 we said was 6. U2 looks like 5. And the cost here is 0. So this has a positive value of 1 so far. That's the biggest number. And last empty cell is row 3, column 1. So we're looking at the formula V1 minus U3 minus the cost in that cell, which is cost 3.1. V1 is 11, U3 is 6, and the cost in this cell is 5, and this zeroes out. So you guys tell me, which cell should we add to our solution? And while you're doing that, I'll change colors so I can highlight it. Yep, we should totally add the cell 2-3 to our solution. Please note, if you have negative values or zeros, you should definitely not add those cells to your solution. And actually, if you get all negative values or zeros, i.e. no positive values, that's how you know to terminate the algorithm. Okay? So here we have one positive value, which tells me this is probably going to be the last step to get the final solution. But it also tells us we want to add in the cell 2-3, so that means our new cell that we want to add in is this guy right here. Okay. Now, once you've calculated who the new cell is that you're going to add in, next you want to go and deal with your loops. Okay. Now, no joke, most people who deal with the loop just draw it in the actual graph. Go for it. What are your questions? Okay. So you always have to what? You always have to include the new cell in your loop, and then all the other cells in your loop have to be currently in the solution. So anybody have a guess what cells are going to be included in that loop? And remember, this is where you looked along the row that your new cell was in and the column that your new cell was in, and looked for exactly one cell in the row in the column that you could throw into the loop, where there was no ambiguity because there's a unique loop that your new cell lives in. Well, if you look along the second row, there's two possibilities, so you can't look along the second row. If you look along the third column, could we actually find a cell to throw into the loop? The answer is hopefully yes. Who is it? Yep, it would totally be 3-3. And that is because 3-3 is the only cell that actually has a solution value in it, or an amount in it right now. Now, once you know that we're dealing with a loop that's currently going to be in row 2 and row 3, row 2 we still don't know which other number to deal with, but row 3, who would be another cell that needs to be in this loop? Yep, 3-2, because that's the only other cell in row 3 that has a solution value in it. Now, once you have these cells in the loop, these 3 cells in the loop, anybody have a guess who the next cell in the loop should be? Yep, 2-2, perfect. Now, I'm not going to lie, for me, 2-2 is not a surprise that it got into this loop. Why? Because in reality, you don't probably want a 0 in your solution. We really wanted to kick both of those 2 cells out last time. So this tells me that that's probably going to be a cell that gets kicked out this time. Okay. Maybe not. Maybe it'll stay there, but we would love to get rid of it. Okay. Sometimes you have to have 0 staying in your solution that you're dealing with. Okay. So let me actually go back and write what we just did down. So we did 2-3, we then did 3-3, we then did 3-2, then we did 2-2. Now, I hadn't been focused in on this, but actually, let's go ahead and mention it. Anybody notice anything about the ordered pairs on these loops as you go consecutive values, or consecutive cells, excuse me? You got it. So what happens is, and this is actually another way to define your loops, is each consecutive next cell in the loop, you're only allowed to change either the I or the J, the first or the second position, but not both. And if you're changing exactly one of the two positions each time, that's a way to guarantee that you actually have a loop in the Tableau, which corresponds to a circuit in the underlying spanning tree. I lie, in what should have been the underlying spanning tree, because you shouldn't have any circuits in a tree. Now, at this point, you go ahead and you calculate this special value theta. The special value theta is always off of your odd vertices. And remember, in terms of values, at 3, 3, we had a value of, what is that, 20? And at 2, 2, we had a value of 0. Oh, no, it was odd. So we take the minimum of 0 and 20, and what value is theta in this case? Yep, it is 0. So that is also a weird situation that doesn't always occur. Normally it is just a number like what we did in our last iteration. So here's what happens if you have 0. So you increase your new cell by 0. That literally means you put a number in the cell and that's all you do. Note, that's all you do anyway is put a number in a cell. But when you then decrease these two cells by 0, what happens? Is there any change to any of the other 3 cells? No. So it's still the 20. It's still the 0. And over here at 10, you should have added the theta. So you add 0 to 10, and it's still 10. Okay? This does happen, and in fact, you don't have to do any of the adjustments like what I did here. You can just leave them blank. I went ahead and put the scratch work in here to indicate that we were still adding and subtracting behind the scenes. You just, when you add and subtract 0, nothing actually changes. Now, you have to decide who you're going to kick out. Okay? You cannot kick out the new cell you just added. That's not allowed. So yes, you look for other zeros, and if there's more than one, you get to pick. In our case, there's only one other 0, so yes, this is totally the time when we are going to remove cell 2, 2. So let me write that down for us. So remove 2, 2 from the solution. And I don't think I have this guy prepped up. I do not. So let me copy and paste. So then our next iteration is we're going to start with this new solution. And let me see if I can't get rid of the extra writing here. All right, so that guy was supposed to be a 0 and a 20. And that would be your new solution. Okay. Notice here, the 0 just got erased, and the 0 got moved over here, which on the face of it seems like there's not much of a change, but it turns out that that was supposed to actually raise our overall or lower our overall cost by 1 unit. Okay. Now, at this stage, we are ready to do the algorithm again. So, repeat algorithm. Now, when we repeat the algorithm at this point in time, notice what will happen when we start looking at this guy. We are going to get the following. I will include the work here since we are basically out of time. We would recalculate all of the U and V's. We would recalculate all of the costs with the tildes. And what we would actually find is that our new edge, and I will include this, I'll go and put in this information after we leave with each other. The new cell that we're going to put in here is actually going to turn out to be 3-1. Okay. Yes, I would expect that you would show the new Tableau and the various equations for each time. So that's why I'm skipping this step right here to show you how, or I guess I should say, when they terminate. So this would be one extra iteration. What would happen is you would have the new guy there. The loop associated with this new guy, and I'm going to on purpose make it so it's going to be easy to get rid of, is going to be this loop. What will happen here is you will add 20, and this 0 will disappear. Okay? So I'm going to go ahead and make a second copy of this guy because the next step is actually the last iteration. Actually, let me go up here and say repeat algorithm. So we'll copy this one more time. And like I said, I'll put in the missing steps that we've had here after class. Now the new Tableau would be as follows. You wouldn't see the loop. The 0 is going to be gone. And these two values are going to be adjusted. So the new values here would be 20, 40, and 20 there actually. Okay. Now at this stage, when we do all of the work, and again I'm going to outline some of it, but I can't outline all of it to answer our questions of how do you stop the algorithm. Okay. In terms of the tildes, we have C11 tilde that we would calculate, C13 tilde that we would calculate, C22 tilde that we would calculate, and lastly C32 tilde that we would calculate. Now you'd have to actually solve for your U's and V's to get those values, but those values turn out to be -3, -5, 0, and -1, and this is the thing that I wanted to make sure to show you. Remember what we were doing with the C tildes right here? The C tildes right here is how we chose our next edge to include in the solution. But what did you want? You wanted the biggest value. In this case, there are no positives, so when there's no positive values left, in other words, you have only zeros and negatives, this tells you to stop the algorithm, and it tells you that your current solution is the optimal solution. Wow, I missed an M. Optimal solution. Now, one of the things people will typically ask is they will ask, what is the cost of the solution? And we talked about that, but we haven't calculated it yet. Anybody remember how to calculate the cost of the solution? It is actually very scalable, but there is specialized software for people who do this a lot. And part of that is because you can actually put these type of tableaus into spreadsheets. And there's add-on packages both for Excel as well as dealing with just specialized software themselves. Now, do they do it by hand? No. But do they have a computer or an add-on package to a computer program that helps them? Yes. But let's finish this off. If you want cost of this solution, and I'll go back in and give you the cost of each of the solutions along the way too and show that this would be the actual smallest one. The cost of the solution would go as follows. This would be 40 times 2 plus 40 times 6 plus 20 times 0 plus 20 times 5, and finish this off, 10 times 6. And this should be, if I added it correctly, this should give us a minimum cost, which is 480, where the actual solution that we were using here is x12 equals 40, x21 equals 40 as well, x23 equals 20, x31 equals 20, and x32 equals 10. Quick check, did you guys catch where the cost of the solution came from. And that's the minimum cost. No, so it's not once all the zeros are gone. The thing that you're looking at is down in those tildes. It's once all the positive numbers are gone. That's the termination thing. Now, it typically corresponds to the zeros in your Tableau being gone, but it doesn't have to. There are definitely cases where you can still have zeros in the solutions. The key thing is these tilde guys, those are going to be either negative or zero are the only options. Yep, and over here, was you totally just multiplied the amount being shipped times the cost it actually took to ship it, okay? Yeah, basically. So neutral tells you include that edge. So this one right here, this 0, 0, this one tells you if you threw in the edge 2, 2, it shouldn't actually change the overall cost of the system. So you throw it in, you don't throw it in, nobody cares. You'll still get an optimal solution. But typically in terms of terminating the algorithm, you'll terminate the algorithm the first time you don't have any positive numbers over there for those C tildes. So that's the complete algorithm. If you guys have extra questions, I'll hang out for a little bit with extra questions. I will plan on posting an additional worked example of one of these guys where everything is put together without all of the extra formulas all embedded, just the question all the way through, okay? But otherwise, that is it for today. That is the complete transportation problem, start to finish over last time, this time.